This lesson is over polynomial function theorems. The fundamental theorem of algebra states every polynomial function of degree n with n greater than or equal to 1 has at least one zero in the set of complex numbers. Every polynomial function p of x of degree n with n greater than or equal to 1 can be factored into n linear factors, not necessarily unique. In other words, p of x equals a sub n times x minus c sub 1 times x minus c sub 2 ... all the way until x minus c sub n. Now to make more sense of this, a sub n is a multiplier. It is a coefficient. It is a number. It does not have a variable. While c sub 1, c sub 2, ... all the way to c sub n are the zeros. Example 1. Find a polynomial function of degree 3 having zeros of 1, 3i, and negative 3i. Well, first, let's identify the zeros. They said it has a zero of 1, 3i, and negative 3i. Now, if we have the zeros, we can find the factors. Now, the factors are always written in the form of x minus the zero. So, if my zero is 1, then my first factor would be x minus 1. My next zero is 3i, which means as a factor, that would be x minus 3i. For the last zero of negative 3i, that would be of the form x minus negative 3i. Now notice x minus a negative comes together and turns it into a positive. So as a function, we write this as f of x equals x minus 1 times x minus 3i times x plus 3i. Now the direction said find a polynomial function. We have a function, but it wants to see a degree of 3, meaning I want to see the highest power as a 3. Currently, we don't see that. We do have our 3 factors, but notice the last 2. There's something very special about these. It turns out these are conjugates, so we're going to multiply these first. Take a moment now to multiply x minus 3i times x plus 3i. As a result, hopefully you found x squared minus 9i squared. Now recall, I squared has its very own value. I squared equals negative 1. So we replace the I squared with the negative 1, and now we need to clean up that binomial. The negative 9 times the negative 1 creates a positive 9. So now we're left with x minus 1 times x squared plus 9. Take a moment to multiply these two together. Hopefully you found f of x equals x to the third minus x squared plus 9x minus 9. Again, order is important. The highest degree should be listed first, working its way all the way down to the constant. Now let's check. In the beginning, it said find a polynomial function of degree 3. We'll check your result. Does it have a degree of 3? Yes. Then we've done exactly what we needed to do. Example 2. Find a polynomial function of degree 4 with negative 1 as a zero of multiplicity of 3 and 0 as a 0 of multiplicity 1. Again, let's start by listing out our zeros. It says we have -1 as a 0, but it says of multiplicity 3, which simply means it's repeated 3 times. So our zeros are -1, -1, and -1. Then it goes on to say, and 0 as a 0 of multiplicity 1, which means 0 is our 4th zero. Now that we have our zeros, we're ready to write our factors. Remember, factors are of the form x minus whatever your 0 happens to be. So first we have x minus -1, x minus -1, x minus -1, and x minus 0. From here, we need to clean up some of these signs or simplify these. So for our function, instead of x minus -1, we can now write that as x plus 1, x plus 1, x plus 1, and then the last one, x minus 0. Well, that's the same thing as x. So here's our function, but again, notice the directions. Find a polynomial function of degree 4, meaning I want to see the highest exponent with a 4. Currently, I don't see that. So since we have 4 factors, we are going to multiply, but let's do it a little bit at a time. Notice the first 2 binomials. Take the time now to multiply those. Hopefully you found the result to be x squared plus 2x plus 1. Now look at the last 2. We have x plus 1 times x. Take a moment now to multiply that. Hopefully you found the result to be x squared plus x. Now we are one step away from having our answer. The next thing is, yes, you will need to multiply this trinomial times this binomial. Take it slowly, but take your time now to do so. Hopefully, after multiplying, then combining like terms, you found the function f of x to equal x to the 4th plus 3x cubed plus 3x squared plus x. Now to check. It said we wanted degree 4. Do we have a degree of 4? Yes. So we're ready to keep moving on. Now let's talk about the rational zeros theorem. This is used to check whether a polynomial has rational roots, which means zeros. It provides a list of all possible rational roots of the polynomial function, specifically of the form p of x equals a sub n of x to the nth power plus a sub n minus 1 times x to the power of n minus 1 plus ... a sub 1 times x plus a sub 0. And we do this if p over q is a 0 of the polynomial, then p is a factor of a sub 0, which is the constant term, and q is a factor of the a sub n, the leading coefficient. In other words, the p of x equals, with all those terms, means the polynomial should be in the correct order. The p-value comes from the constant. The q-value comes from your leading coefficient. Let's look at an example. For example 3, it says list all possible rational zeros of the function f of x equals 15 x to the 6th plus 46x squared plus 2. Now, because it says list all possible rational zeros, rational means fractions, which means we are talking about p over q. Now, the p-value comes from where? It comes from your constant, which means it will be coming from a factor of 2. Now your q value comes from what value? Well, your leading coefficient, which in this case is a 15. So it will be a factor of 15. From here, we have to list all possible factors of these values, including positives and negatives. So let's start in the top. Factors of 2. Can 1 divide into 2? Yes. So we include the positive and the negative 1. Can 2 be a factor of 2? Yes, which means we include the positive and the negative of 2. We found all possible factors of 2. Now we're going to find factors of 15. Can 1 go into 15? Yes. Can 2 go into 15? No. How about 3? Yes. 4? No. 5? Yes. 6, 7, 8, 9, 10, 11, 12, 13, 14? How about 15? Yes. So we have found all the factors of 15. Now it says list all possible rational zeros. That means every possibility. So here's what we need to do. We look at the 1 on the top, and we're going to put a 1 over each of the numbers in the bottom. So 1 divided by 1 could be 1 or negative 1. 1 over 3 would be a positive 1/3 and a negative 1/3. 1 over 5 or a negative 1 over 5. 1 over 15, negative 1 over 15. So we found every possible combination in dealing with the 1 in the numerator. Since we've used all possibilities, we mark out the 1, and now we do it with the next factor, which in this case is a 2. So 2 over 1 gives you 2 or negative 2, 2 over 3 or negative 2 over 3, 2 over 5 or negative 2 over 5, 2 over 15 or negative 2 over 15. Now in this particular case, none of the values repeated, but in the future, if any of your values do repeat, there is no need to repeat them. Once they're in the list, you're good to go. Now, we just talked about finding rational zeros, which means zeros that may be written as a fraction, but there are other zeros too. The first one is called irrational zeros, and they will appear in conjugate pairs. An irrational zero is of the form a plus c square root b, will also be paired with a minus c square root b. What makes them conjugates is that one has a plus and one has a minus. So to make sense of this, a numerical example would be 1 plus square root 3 and 1 minus square root 3. Next, we also have non-real zeros. Non-real zeros will also appear in conjugate pairs. Now, non-real means it must be imaginary. So we have a plus bi and a minus bi. Again, to look at an example, that possibly could be of the form 2 plus I and 2 minus I. Overall, the clues to look for is if you see a square root, then automatically you will have its conjugate pair. The other option is if you see an I, it too will appear in conjugate pairs. Let's look at an example. Example 4. Find the remaining zeros of a polynomial function of degree 5 that has 1 plus square root 3, 4i, and negative 2 as a zero. So first we want to list out the given zeros. The first 0 is 1 plus square root 3. Next we're told 4i, and we're also given negative 2. Now it says find the remaining zeros, so we have to look for other zeros. Here's what we do. We look at the first 0 given and we ask, do we see a square root? And we do, which means we automatically have to include its conjugate. Since this one was 1 plus square root 3, the conjugate must be 1 minus square root 3. The next 0 we were given was 4i, and so we look. Do you see a square root? No. Do you see an I? Yes, which means automatically we must include its conjugate. Since this is a positive 4i, its conjugate would be negative 4i. We look at our next 0 of negative 2. Do you see a square root? No. Do you see an I? No. So, since there's no square root and no I, that means there's no conjugate. These are all the zeros. To check, notice it says it was a polynomial function of degree 5, which means we should have 5 zeros. If you count the given zeros and the other zeros, notice we have found all 5 of them. Example 5. Given f of x equals x to the third plus 3x squared minus 2x minus 6. For part A, it says find the zeros, rational and others. Part B, factor f of x into linear factors. So starting with part A, finding the zeros. Well, looking at the problem, first thing we want to do is, because this is not a quadratic, is we want to use some of the tools we've been learning. The first thing would be we need to do p's over q's. P, remember, is your constant term. Q is your leading coefficient. Take a moment now to list all the possibilities for P over Q. Hopefully you found all the possibilities to be 1, negative 1, 2, negative 2, 3, negative 3, and 6, negative 6. Now this is just a list of possibilities. These are not guaranteed. So from here, step 2 is we type the original equation into your y equals screen on your calculator and then click graph. We're going to let the graph help narrow down from our list. So take a moment now to graph this on your calculator. Hopefully your graph looks something similar to mine. Now that we have the graph, we analyze it. What values from the list appear to be x-intercepts on the graph? Well, notice our graph appears to have 3 separate x-intercepts. Starting from the left, what x-intercept does that appear? Does it appear to be a value in our list? And it does. It appears to be negative 3. The next x-intercept, notice it does not appear to be on a number, it appears to be fractions. Do we have any fractions in our list? No. We look at the last x-intercept along the right side. It too appears to be a fraction, but we do not have any fractions in our lists. So far, negative 3 looks to be the best option. But what do we do with it? Well, step 4 is we use synthetic division to confirm if whether or not negative 3 is a factor. So let's set up our synthetic division. Remember, for synthetic, we use the coefficients from the original function, which means we would have a 1, 3, negative 2, and negative 6. The number in the corner would be -3, and that's the number we're trying from our list from P's over Q's. Now take a moment now to do your synthetic division. Remember, you bring down your first value and then you multiply and you add, multiply, add, multiply, and add. And then once you've done that, the last value is separated. Now we've done all this division, but what does this mean? Well, the value on the right side is your remainder. The numbers on the left side are your quotient. Now the question is this a 0? Yes, since our remainder is 0, that means that -3 is a 0 of the function, which means x plus 3 is going to be a factor. Now to find the zeros means we must set the function equal to 0. So we have the original function, and where you see f of x, we simply place a 0. Now remember, we just did synthetic division and we found a factor. So our factor was x plus 3. But what are we left with? Well, look at the quotient. We have the coefficients, which gives us x squared minus 2. So looking at our equation, we have some number times some number equals 0, which means we can set each piece equal to 0. The first piece, x plus 3 equals 0, can be solved by simply subtracting 3 on both sides, and we find x equals -3. The other possibility is x squared minus 2 equals 0. Notice we only have x squared and no x terms, so let's isolate x squared. To do so, we add 2 to both sides, and then we take the square root of both sides. That gives us x equals plus or minus square root 2, but we must separate these, which gives us x equals square root 2 and x equals negative square root 2, which means we have now found all the zeros. Our zeros are -3, square root 2, and negative square root 2. For part B, it says factor f of x into linear factors. Well, we know that factors are of the form x minus the 0. Since we know the zeros, we do know the factors. So f of x is equal to x plus 3, x minus square root 2, and x plus square root 2. And that is the result for part B. Now, we are going to extend this problem a little beyond than what it asked for. The extension is we are going to graph this. We are going to look at its end behavior, the x-intercepts or zeros, the y-intercept, and we need to remember how to do interval testing. So let's start with the end behavior. Remember, to identify the end behavior, we have to look at the leading term. Since x cubed is raised to an odd power, that means opposite directions. Since it's positive, it will not flip, which means on the left side, it will be going down. On the right side, the graph will be going up. For the x-intercepts, well, these are points on a graph. These depend on your zeros. Since we have 3 zeros, we will have 3 x-intercepts. They are -3, 0, square root 2, 0, and negative square root 2, 0. To find the y-intercept, we substitute a value of 0 in for x, and when you do so, all the x terms will cancel, which leaves you simply with the constant. So the y-intercept would be of the form 0, -6. Now we're ready to do the interval testing. This is where you draw your x-axis. Now since we have 3 zeros, we have 3 specific values on the x-axis we must mark, and they do need to be in the correct order. The smallest value that appears furthest on the left would be -3. Next would be -√2, and then next would be +√2. Now these values are your x-intercepts, but we must choose values in each of these sections. Now there happens to be 4 sections. So we need to choose a value to the left of -3. Maybe you're thinking -4. Next, I need to choose a value between -3 and -√2. If you do not know -√2, feel free to type that value in, √2, to find its decimal approximation. You should find it to be -1.4. So choose a number between -3 and -1.4. You're probably thinking -2. The next region, pick a value between -√2 and +√2. Maybe you think of 0. And then a value to the right of √2 or a value to the right of 1.4. Maybe you'll find 2. So what we've done is we've chosen x values. Now we want to use the calculator, the table feature, to find the corresponding y or function value. Using the table, hopefully you find when x is -4, the result is -14. Now the purpose of the interval test is to tell you characteristics. I plug in a -4, the result is -14. Am I going to be above or below the x-axis? Well, -14 means it will be below. The next region, when x is -2, y is +2. Since it's positive, the graph will be above the x-axis. When x is 0, y is -6. Since it's negative, it will be below the x-axis. When x is 2, y is 10, which means it will be above the x-axis. Now we're ready to graph this. Feel free to draw a t-chart and collect all your ordered pairs from the interval test so that it's a bit more organized. Okay, so we have our x and y axis. Take a moment now to plot all the points that you can on the graph. Hopefully, your graph looks something similar to mine. Now, since we have the graph, check, does it match the end behaviors? Yes. Does it appear to have the same x-intercepts? Yes. Does it appear to have the same y-intercept? Yes. So, I think we did a pretty good job. Example 6. Given g of x equals 3x to the fourth minus 4x cubed plus x squared plus 6x minus 2. For part A, find the zeros, rational and others. For part B, factor f of x into linear factors. For part A, looking at the function, notice we cannot factor this. We cannot do factor by grouping, no AC method. There's nothing we can do. So what we do is we start with our P's and Q's. Take a moment now to identify your P and Q values and find all the possibilities. Hopefully you found the possibilities to be 1, -1, 2, -2, 1/3, negative 1/3, 2/3, negative 2/3. From here, we now type in the original equation into your calculator on the y equals screen. Once you've typed it in, click Graph so we can look at the graph to analyze the information. Hopefully your graph looks something similar to mine. Now that we have the graph, what values from our list of possibilities appear to be x-intercepts? Well, reading the graph from left to right, the first x-intercept appears to be at what value? Well, it appears to be at -1, which is in our list, so we make note of it. The other x-intercept appears to be a fractional value. Now that fraction appears to be closer to 0. Do we have any fractions? Yes, we have 1/3 and we have 2/3. Since 1/3 is a smaller value and closer to 0 than 2/3, there is a good chance the 1/3 might be a possibility. So how do we confirm this? Well, we have to use synthetic division to confirm. We cannot just look at a graph and automatically assume that it is going to be a 0. So we set up our synthetic division. Remember, we only use the coefficients from the original function, which means we have 3, -4, 1, 6, and -2. For the first value, you're probably wanting to use the whole number or the integer. Let's start with -1. Take a moment now to do synthetic division. After doing synthetic division, we look at the results from it. Remember, your last value to the right will be your remainder, and the numbers on the left represent your quotient. So looking at the result, what does that tell us? Is -1 a 0? Yes. Since the remainder is 0, that means -1 is a 0, which also tells us x plus 1 is a factor. Now, we are trying to find zeros, which means we would take the function and set it equal to 0. We just did synthetic division and we found a factor, which means 0 equals, and then we take out the factor we just found, x plus 1. But what are we left with? Well, we're left with the quotient, the numbers 3, -7, 8, and -2. Well, those are your coefficients. That means we're left with 3x cubed minus 7x squared plus 8x minus 2. Now we're ultimately trying to factor this. We have factored out the x plus 1, but the second piece, the 3x cubed minus 7x squared plus 8x minus 2. We would try to factor by grouping because it has 4 terms, but it turns out it does not factor that way. So what do? Well, it means we need to try synthetic division again. But this time the values that we use are the coefficients of the quotient. So we will have a 3, -7, 8, and -2. Why is it the quotient? Because that's the piece we're trying to factor into smaller pieces. Now for our value in the corner, did we have any other numbers that appeared in our list of possibilities? Yes, that value was a 1/3. So we are going to do synthetic with 1/3. So remember, we bring down our first value. 1/3 times 3 gives us 1. -7 plus 1 is -6. 1/3 times -6 is -2. 8 plus -2 is 6. 1/3 times 6 is 2. -2 plus 2 is 0. So we've done the division and now we analyze it. Is 1/3 a 0? Yes, since the remainder is a 0, that means that x minus 3 is a factor. So again, that means we have 0 equals x plus 1 from our first synthetic division, and we just found x minus 1/3 is also a factor. But what are we left with now? Well, we're left with the coefficient of our quotient, 3, -6, and 6, which means we're left with 3x squared minus 6x plus 6. So here's where we left off. We are slowly shrinking this polynomial function down, but we're not quite done. The last piece, the 3x squared minus 6x plus 6. Well, notice that's a quadratic. We have many tools to use when dealing with quadratics. We'll look at those three terms. Do they have anything in common? They do. They do have a common factor, and that common factor happens to be a 3. So a factor a 3 out of the quadratic, and that would leave me with x squared minus 2x plus 2. Now, we have factored it. Our focus is on that last piece, that trinomial. If you try to factor x squared minus 2x plus 2, it turns out it cannot be factored. So what do? Well, this is all some number times some number times some number equals 0, which means we can take the time to set each piece equal to 0. The first piece, x plus 1 equals 0. If we were to solve for x, we find x equals -1, which we already knew from synthetic division. The next piece, x minus 1/3 equals 0. We solve for x by adding 1/3, so x equals 1/3. Again, we already knew that from synthetic. The next piece has 3 equals 0. Is that even possible? Is 3 the same thing as 0? No. Notice there is no variable, which means the 3 is simply a multiplier. It's not a 0. So don't worry about that piece. The last piece, x squared minus 2x plus 2 equals 0. It's not factorable, so what else can we do when it's a quadratic? Well, it means we will need to use the quadratic formula. So take a moment now to find the quadratic formula and plug in your a, b, and c values. Once you've plugged in your values, go ahead and simplify and see if you can find your zeros. Hopefully, as you simplified, you noticed you had a negative under the radical, which means an I was introduced. You separate the real from the imaginary, and then reduced each piece, which gives you 1 plus or minus I. Now we must separate these, which gives us x equals 1 plus I, and its conjugate, which is x equals 1 minus I. Now, this means we have officially found our last two remaining zeros. So we can finally answer part A. Our zeros are -1, 1/3, 1 plus I, and 1 minus I. Now part B was to factor it into linear factors, which means g of x equals 3, our multiplier, times x plus 1 times x minus 1/3 times x minus 1 minus I times x minus 1 plus I.